This is part 2 of a demonstration for the Week 7 lab with ECET 105 through DeVry University during the fall semester of 2015. In this lab, we were asked to enhance an adder-subtractor circuit that we previously built in Lab 5. In that circuit, we designed an adder-subtractor that took two binary inputs and displayed the binary output of the addition performed with both of those inputs. The original circuit did not have displays to show us what the inputs were going into the adder-subtractor circuit. All we had was a display coming out, which was RD0 through RD4. The first four red LEDs on the right hand side above switch 1 would tell us what the binary value was of the addition, and then RD4 would let us know if the total addition exceeded the ability to be displayed and would give us a carry bit signal. In the previous build of that circuit, it had already been enhanced to give us a display of what the inputs were so that we were able to visually see what we were putting in on the dip switches to make sure that they were making contact. We also made it possible that whenever we engaged the subtraction portion of the circuit, that RD7 would light up and let us know that we were performing subtraction instead of addition. With the enhancements that we are making to the current circuit, we're still going to see the same items there. We're wanting to see that with any of the inputs that are being put in on switch 1 or switch 2 using the first four dips, we should see the green LEDs above each of those switches light up with a corresponding binary value. Right now we can see that on switch 1 we have dip 0 and dip 2 are set to high. This gives us a total binary value of 5, and if we look at the green LEDs above it, we can see that they correspond appropriately. With switch 2, we can see that dip switch number 10 is set to high. This gives us a single binary value of 4, and the green LEDs above it show the same thing, that we have one LED on in the third position, giving a binary value of 4. The other portion that we're seeing is that RD3 and RD0 are lit up. Part of the previous testing of this circuit, that was the final state of Q on the flip-flops that were used to enhance the circuit, and we'll talk about that a little bit more, but we're going to go ahead and clear that out of the way. When we do this, you'll notice that RD5 turns off, and when we release the clear function, RD5 turns back on. RD5 is a visual enhancement that was added during the Week 7 lab. This made it possible for us to see whenever the clear function was being engaged on the circuit. This was helpful for testing the circuit as we were developing it and placing it onto the board to ensure the fact that all the functions were working correctly and that our buttons were connected in appropriate places. You saw that our DB1 button cleared the lights that were on RD0 and RD3, which were giving us a display value of 9 in binary. At the top, you can see that our 7-segment display is still showing a 9. The reason that this is happening is because the adder subtractor is passing the binary value of 9 to the flip-flops that are controlling RD0 through RD4, and the 7-segment display is sampling the information that is being passed to the flip-flops before the flip-flops actually receive it. So anytime that we put in any values on switch 1 or switch 2, we should see immediately whatever our output is going to be in decimal value on the 7-segment display up to a value of number 9. With the items that we have here at the moment, the other thing that was important to note is that seeing the value show up on RD0 through RD4 requires us to enable a clock pulse. Some of the testing we had done previously, and in the previous lab, we generated a clock pulse with a function generator and then passed that clock to the flip-flops that we were testing. With this circuit, we are manually triggering the clock pulse ourselves because it's going to help us to perform a function similar to how a calculator would work. Whenever you're typing in numbers on a calculator, you do not want to see the calculator constantly updating itself and showing you the value of whatever it is that you're passing in. You wait until you're finished typing in your input values and you press the equals key, and the equals key, once it's pressed, will then perform whatever function that you have requested with whatever values that you gave the calculator and display the finished product. Similarly, we want to see the same kind of thing here. So whenever we enable the clock pulse, whatever value is being passed to the D flip-flops at that time will show up on RD0 through RD4. RD4 is our carry bit and lets us know that we have a carry bit being passed. RD0 through RD3 are going to be the binary value of the addition or the subtraction that's being done. RD6 is going to let us know whenever we have a high enabled on the clock pulse, and RD7 lets us know whether or not we're performing addition or subtraction. If the LED is turned off, we're performing addition. If the LED is turned on, then we are performing subtraction by inverting whatever number is being placed on switch 2. So we're going to test a couple of these functions real quick and see how well they work. Again, we're going to see an update on the 7-segment display immediately as we're changing any numbers or changing the function of what the adder subtractor circuit is doing, but we should not see anything display on RD0 through RD4 until we press DB0, giving a clock pulse. Once we're finished passing information to the D flip-flops and displaying that information on RD0 through RD4, we should be able to clear whatever that information is with DB1, the same as we did earlier in the video. So we're going to give this a test now. We're going to go ahead and pass the information that we have now. We should have a value of 9 being passed to the flip-flops. We're going to test our clock function and press DB0. We can see that RD6 is lighting up while I'm holding the button down, meaning that there is a high on the clock. When we let go, RD6 turns off, RD0 and RD3 stay on, showing that we're passing a binary value of 9 to the flip-flops. Right now, the Q values are staying in place because we have not sent any new information to the flip-flops, and even if we had, we haven't sent a clock pulse to pass that information to the Q outputs. It's something that's significantly important, and we're going to show how that works here. We're going to change from addition to subtraction, and we'll see when that happens that the value on our 7-segment display will change immediately. We should get a value of 1 because we are subtracting the number on switch 2 from the number on switch 1. The binary value that's passed on switch 1 right now is the number 5, and the binary value of switch 2 is 4. So we should show 1 on the 7-segment display, but we shouldn't see any changes at all. With RD0 through RD4. And we can see that happened. RD0 through RD4 is still showing that we have a binary value of 9 on the flip-flops, but at the top the 7-segment display shows us that the binary value being passed out of the adder subtractor circuit is a 1. So there are two things that we're going to attempt here. We're going to press the clear button and make sure that the signal from the clear is not doing any other adverse functions, or it is going to end by passing information to the output. If that were to happen, if we were to press the clear button and get a change in our value for the output, then that means that we are somehow triggering the clock pulse, which we shouldn't be doing, or that there is another potential function wrong, but we're going to take a look and see. So we press DB1, and we see that the LED is turned off for RD0 through RD4. As that happened, you saw that RD5 turned off while the button was pressed, and whenever we released it, RD5 turned back on. We still see that RD7 is turned on, showing that we're doing subtraction with the circuit. And we now have no display showing on RD0 through RD4, which is exactly what we were expecting. Now we're going to test and see if we can pass the binary value 1 through the flip-flops to the Q output by triggering our clock. We can see that we have RD0 turned on, letting us know that we have a binary value of 1 being passed through, and there's a carry bit being passed on RD4. We're going to test one more set of numbers. We're going to change the binary value of switch 1 to a value of 2. So this will require us to turn off the 2 that we currently have. We're going to change the value on switch 2 to 3. We're going to turn our subtraction off so that we're doing addition. We can see on the 7-segment display that we're now showing a value of 5. The lights on RD0 through RD4 did not change while we were doing any of those functions, which is exactly what we expected our circuit to do. Nothing should happen until the point where we press DB0 and attempt to enable the clock. So let's do that. We should see an update happen on our display for the LEDs. We saw RD6 turn on momentarily while the button was being pressed, and our binary value being output to the LEDs is now showing RD0 and RD2 is turned on, giving us a binary value of 5. This matches what we're seeing on the 7-segment display, showing that we're passing information correctly to the flip-flops, and that those flip-flops are correctly passing the information onto the LEDs. We're going to attempt the clear function one more time, which worked exactly as expected, turning off RD0 and RD2. So this is the enhancement of that circuit, and again, this is very similar to the functions of a calculator. We can see how this would be applied in that type of circumstance or nature. Otherwise, this has been pretty informative. I'll see if I can do something about uploading the schematics that show the enhancements that I've made for the extra visual outputs. Again, they were very helpful for debugging the circuit as we were going through and adding the features for the D flip-flops. Have any questions? Leave them in the comments. Thanks.